Today we are going to talk about Introduction to Remote Sensing course, where actually we talk about different types of orbits under the title as Geometry of Remote Sensing. So typically within the space we see these satellites moving around that surface in a fixed curved path, what typically we define as orbits. Orbits, within the orbits, satellites are moving with the gravitational pull of the Earth's surface. So typically how we define orbit? Orbit is the specific path that is followed by the satellite which is moving around the Earth or any other celestial body. So the closer the satellite near to the Earth, it actually moves with a very high velocity. So when you talk about the orbit, we call as a orbital plane and orbital period. So the plane in which satellite always moves is actually called as an orbital plane, and the time taken by the satellite to come to the same position or completing a full cycle, what we call as an orbital period. So depending upon the type of the rotation of the satellites within the orbit, we categorize satellites into two categories, or the orbits into two, as prograde and the retrograde. So usually within the orbit, when the satellite is moving in the same direction like that of the Earth rotation, we call this as a prograde rotation. While in some cases satellite moves in opposite direction to the Earth rotation, that's actually what we call as a retrograde orbits. So now we can classify orbits into two categories as circular orbits and the elliptical orbits. So circular orbits actually have a fixed distance from the surface of the Earth, and within these orbits satellites move with the same kind of velocity. While if you look into the elliptical orbits, actually here the satellites are something far away from the Earth's surface, and sometimes they become very close to the Earth's surface. So now we see a kind of close satellite coming very close to the Earth and sometimes very far from the Earth's surface. So now when it comes very close to the Earth's surface, it has to overcome the Earth's gravitational force. As a result, the satellite moves with a very fast, because it has to overcome the gravitational pull of the Earth's surface, else actually it may move out of the orbit. While when it is in the farthest place, the velocity may be less because there is a less gravitational force. Further, if you look into the concepts of the orbits, typically we have something called radius. Radius is the distance between the Earth center to that of the orbit. So if you look into the circular orbits, the distance or the radius is almost remains constant. While if you look into the elliptical orbits, the distance from the surface of the center of the Earth to the orbit, actually there is a variation. So geocenter is the location, exact center part of the Earth, from which actually we see the calculating the radius of the orbits. So now these orbits are placed within a fixed inclination or the angle within the space. So the inclination angle is actually passing through the geocenter, and we have different types of inclinations for the different types of orbits. When you talk about the elliptical orbits, something important is that we will talk about two terminologies. One is the apogee and another is the perigee. Apogee is the longest distance from the satellites to the center of the Earth. while perigee is the shortest distance from the earth to the orbit. So, whenever there is an apogee and perigee, because the satellites are constantly moving within the elliptical orbits, and during the perigee time they come very close to the surface, while during the apogee they are far from the center of the earth. So, depending upon this kind of variation, the velocity of the satellite changes. So, now an orbit is defined by three factors basically. One is the shape of the orbit. So, orbits can be circular or they can be elliptical. So, in case of elliptical, as I mentioned, the velocity is actually there is a variation within the orbit, while in case of the circular orbits the velocity remains same. And altitude of the orbit, mostly if you see the circular orbits, they are placed at a very high altitude compared to that of the elliptical orbits. Then we have the angle of the orbital plane that makes the equator. So, this is the angle of inclination. So, this is actually the inclination angle. It mostly varies with reference to the elliptical orbits, while in case of circular orbits it remains almost 0. If you classify these orbits based upon their altitude, we can categorize them into three as high earth orbits. So, high earth orbits or the HEO, these are the orbits which are actually placed at a very high altitude, and typically these kind of high earth orbit, they are typically used for the weather monitoring. So, satellites are placed in these high earth orbits that typically help us in monitoring frequent weather parameters. While then we have the medium earth orbits, which are something below the high earth orbits, and they are typically used for the navigation purpose. So, mostly what we see the GPS constellation of the satellites, they are mostly present in these medium earth orbits. Then we have the LEO or the low earth orbits. These are the orbits which are very close to the earth surface, and typically whatever the remote sensing satellites that are typically capturing information about the surface of the earth related to forest or any other thing, they are placed in this LEO or the low earth orbits. So, finally, we have these satellites, they are designed in any one of these basic orbits. So, we can have some in the high earth orbits, some in the medium earth and some in the low earth orbits. So, if you look into the high earth orbits, typically we use the word geosynchronous. So, synchronous actually having the same thing with respect to that of the earth, geo is the earth. So, mostly these are the satellites that orbit with the same speed as the earth rotates. So, these orbits has the same kind of velocity, something similar to that of the earth. That is why we are using the word geosynchronous. They are actually synchronizing along with the earth surface. So, mostly these geosynchronous satellites, they almost complete one sidereal day, that is around 23 hours 56 minutes and 4 seconds. So, they take one rotation to complete one sidereal, that is to come to the exact same position they took around 23 hours 56 minutes and 4 seconds. So, mostly they have the inclination with respect to the equator. Inclination is the angle that is made by the orbits with respect to the equator. So, mostly these geosynchronous actually they incline with respect to the equator, and sometimes they have 0 degrees angle. And mostly these high earth orbits, they are actually the circular orbits which are actually placed above the equator. So, in short we can say a geosynchronous satellite is the earth centered orbit with an orbital period that matches exactly with that of the earth surface. As I mentioned, so the time taken by the earth rotation is something same what we see with respect to this geosynchronous orbit. So, the geosynchronous orbit, they maintain the high velocity similar to that of the Earth, so that they may not be deviated from the Earth's surface. So, examples of these satellites include ML 300K, EchoStar and Galaxy. So, with respect to these high Earth orbits, again we have terminology, that is the geostationary orbits or the geostationary Earth orbits. So, the satellites that are placed within these geostationary orbits, they have the same direction as the rotation of the Earth. So, what I mentioned in the starting, the prograde, the direction of the Earth rotation and the direction of these geostationary satellites is something similar. So, they rotate along with the same, that is why we use the word geostationary. So, the stationary watch is typically that for an user, it always looks something that the same location, because it is moving along with the Earth at the same pace of speed. So, if you look at the stars, how stars appears for us as if they are actually stationary, something we see the same with case of these geostationary satellites. So, the law of geometry actually dictates that the orbit consistently remains fixed over the same location on the Earth surface. So, we have Earth and above that we see this geostationary orbit. So, how this orbit is placed? As per the law of geometry, it remains at the same. So, it must move same along with the rotation of the Earth. So, it aligns its rotation similar to that of the Earth rotation. Hence, for an user, it appears something like a stationary. So, the Indian national INSAT, what we call as the Indian national satellites, which are largest domestic satellite group, communication satellites, typically they operate in this geostationary orbits. So, example of this is the Intelsat, Kalpana, Medsat and other come under the category of these geostationary orbits. So, if you look into this picture, we have the green representing the geosynchronous, while the red represents the geostationary. So, geostationary actually the satellites complete the same rotation with the 24 hours, while if you look into the geosynchronous, though it appears passing from the center of the Earth, so it takes one half to cover the top and another half in the second one. So, this is not actually the one which is the stationary. So, we have this geostationary orbits that typically helps us in monitoring the weather parameters. So, if you look into the details of geostationary satellites, they are typically placed at an altitude of 36,000 kilometers above the equator with the inclination angle of 0 degrees. So, positionally in a geostationary orbit. So, in these geostationary satellites, they are placed in the geostationary orbits. That is why they actually move along with the Earth's same speed and helps us monitoring the particular location continuously. That is how we will try to monitor the weather parameters. So, providing continuous coverage over the specific region. So, since the satellite is looking at the same position and moving along with the Earth at the same speed, they help us in getting the continuous information about that particular location, and at the same time we get the images at the short intervals, that is for every 15 minutes or 5 minutes or 10 minutes, it actually captures the information about that particular location more frequently. So, if you look into the any kind of cyclone or some kind of flooding scenarios, where actually we get at different time intervals of the satellites, that helps us to monitor that whether the cyclone is moving in which direction. So, typically geostationary satellites helps us in this kind of information. So, advantages of geostationary satellites is they provide a continuous coverage information of a particular location, and they look at the particular point, fixed point of the view, continuously monitoring a single place, and wide coverage. So, since they are placed at a very high altitude of 36,000 kilometers, they cover actually very large area. So, they cover large area and give information about that particular location continuously. That is a typical advantage of geostationary satellites. So, what are the applications of these satellites? Typically, they help in the telecommunication. So, whatever the communication related to the signal process that is coming from these geostationary satellites, broadcasting of the TV, radio and other things are typically coming from these geostationary satellites. Weather monitoring, as I mentioned, since they look into the position of a particular location continuously, we can monitor the weather and other parameters. It also helps us in monitoring the environment, because we get images of different time periods. We can trace out what are the changes that are happening in that particular location. So, for that purpose we can make use of these geostationary satellites. It also help in the disaster management. So, during the disaster management we can have the pre and the post images, and also at different times during the time of disaster also we have the images where we can assess what is the extent of the damage happened and where actually we need to focus for the help purpose. Navigation and positioning, since they are placed in the high altitude, they also help in getting the communication and for the navigation purpose. Though directly they are not helping in the navigation and positioning, because we have GPS as one of the main component that provides the navigation process, but geostationary satellites, they augment the signal. They actually act as a supporting for the GPS system, but does not directly involve in the navigation and the positioning process. And finally, for the different scientific research purpose, so to identify the pattern of the cyclone, or to identify the flooding scenarios, or to identify the climatic conditions of a particular location, typically we can make use of these geostationary satellites. So, now what are the challenges that are actually involved in these geostationary satellites is the limited coverage. Since they are placed above the equator, so the inclination angle covers a minimum latitudes of the particular area, while sometimes or mostly the poles are ignored. So, we don't have any information related to the north or the south poles, because they are placed above the equator and the inclination angle does not cover the other parts. So, that is one of the major challenge with respect to these geostationary satellites. Then signal delay, because the signal has to travel from the satellite to the ground and from ground to the satellite, making a twice movement of the signal, that is takes around 71,600 kilometers they have to travel with the speed of 3 into 10 to the power of 8 light velocity. So, there is a lag delay in the signal that actually brings the some kind of lag in the communication process. And the building, launching and maintaining these kind of geostationary satellites is also something expensive. So, these are the typical challenges that usually we see with respect to geostationary satellites. Then we have medium Earth orbit, where actually these are the satellites which are, this is a orbit which is something below the high Earth orbit, mostly observed between the 2000 to 36,000 kilometers. So, where actually they are in the medium below the high Earth orbits. So, these medium Earth orbits are typically we have two categories. One is the semi-synchronous orbit. This semi-synchronous orbit is a near circular, not totally the circular one. So, as I mentioned, we have circular and elliptical. So, mostly in the high Earth orbits, we typically have circular orbits, while in case of the medium Earth objects, we see actually a near circular orbits, and they are placed at around 20,200 kilometers above the surface of the Earth. So, this satellite actually it takes 12 hours to complete one rotation. If you see in case of the geostationary satellites, it takes 24 hours to cover the location particular area, while in case of this semi-synchronous, it actually takes 12 hours to complete the orbit. That means actually it crosses twice at the same location. Suppose there is a next location, so it can travel twice with 12 hours, within 12 hours it travels twice and covers that particular location. So, this orbit is typically where we see the use for the global positioning system. So, the GPS system, which is the constellation of different satellites, all these satellites are placed in this semi-synchronous orbit. Here we have a special kind of orbit called Molniya orbit. This Molniya orbit actually it is a highly elliptical orbit. As you see in semi-synchronous, it is a near circular. This is a highly elliptical orbit. It is stretching wide with a height of inclination around 63.4 degrees. That is the inclination angle. So, when you talk about the inclination, that is how they are placed with respect to the equator plane. So, this Molniya orbit actually developed by the Russians to overcome the limited coverage of the geostationary satellites. As I mentioned previously, geostationary satellites cover a limited latitude region. Mostly they will not cover the southern pole or the northern pole. So, to overcome such kind of problem, this Molniya orbit is designed where actually it covers the information about the polar regions more frequently, and this is the primarily used by the Russian for its communication satellites. So, if we look into more detail of the Molniya orbit, it is almost highly elongated shape, elliptical, as I mentioned, is an highly elliptical one, where actually it spends major area at the other end, while it is very close is the another end. So, in total this satellite in Molniya, so this is the Molniya orbit. The satellites in the Molniya orbit complete one full rotation orbit for 12 hours with approximately 2/3 of the area spent over the time of the single hemisphere. So, it spends more time in the this hemisphere, while it has a less time in this, because when the satellite moves, it spends more time in this part compared to that of the other side. So, it covers more information on this part of the polar region. So, this is mostly for the communication purpose for the northern and the southern regions, which is actually one of the main drawback what we see in the geostationary satellites, and is a classical example of the high elliptical orbit. So, it is not high earth orbit, it is the example for the high elliptical orbit. So, example for this we have Navstar 66 and Russia GLONASS and China CAMPUS. So, satellites of this navigation process are placed in this Molniya orbit. Applications related to this medium earth orbit. So, it typically facilitates the global positioning system. So, mostly all the GPS satellites are typically placed in this medium earth orbit, and also for the navigation in the communication systems for the mobile satellite communications. So, what are the challenges with respect to medium earth orbits? They are more prone to radiation and the atmospheric drag, which can impose a limitation on the satellite's lifespan. So, because of the interaction with the vulnerable radiation within the atmosphere, there is a possibility of threat to the lifespan of these satellites. Furthermore, these are actually not in a fixed position relative to the earth surface like a geostationary. Geostationary they have fixed with the respect to the earth, while these medium earth orbits they are actually not fixed, they keep on actually moving their orbits location. So, when they move their orbit location, there is a process of actually tracking the communication forms something a difficult one. So, this dynamic nature necessitates the more sophisticated tracking and communication systems to maintain consistently connective, which is not actually positive when the orbit is frequently changing. So, this is one of the drawback with this kind of medium earth orbits. Then we have low earth orbits. Low earth orbits are something very close to the surface of the earth. They are typically located between 160 to 1500 kilometers from the surface of the earth. Since they are at the very near to the earth surface, there is a possibility of getting a very good high resolution data sets, because it is very close to the surface. So, these orbits and the satellites within these orbits actually captures a very high resolution, very high spatial resolution data sets. So they have short orbital period between 90 to 120 minutes. While if you see look into the geostationary and the other high Earth orbits, which is having 36,000 kilometers, and the medium Earth orbit, which is the 12 hours. Here the orbital period. So when I say the orbital period, it is the time taken to come to the same location. So here it is something around 90 to 120 minutes. So the lower altitude actually causes the high velocity, because when the satellites in this orbit, when they come very close to the surface of the Earth, there is a gravitational pull from the surface of the Earth. So to overcome this kind of gravitational force, these satellites they have to move with a very high speed. So the lower altitude actually makes the satellites to move with the high velocity to counteract the Earth gravitational pull. And typically the velocity is around 8 kilometers per second that is required, resulting in the orbit to rotate in the around 90 minutes, although it varies according to the different satellites, because satellites are placed between 160 to 1500 kilometers. So depending upon the height actually we see that there is a variation in the velocity. So mostly 50% of these satellites what we use for the scientific research are typically placed in this low Earth orbits. So now we have something with respect to low Earth orbits. We have polar and the near polar satellites. So some satellites within these polar orbits, they actually pass through the poles to pole from the they have the inclination of degree of 90 degrees. So these they make a rotate from north pole to south pole. As a result, we see that when the satellite is moving, we call this an ascending path, and again when the satellites move down, there is a descending path. So satellites makes one ascending and one descending path. If the satellite is something near polar, that means not exactly 90 degrees, there is a variation in the inclination angle. So we see this again for them also, the ascending and the descending path. So when there is an ascending path, it actually does not capture information, while during the descending path the satellites they capture the information. So mostly when the satellites are in the sun synchronous means the satellites they cover the area and come to the same location at the same local time. Suppose if the satellite is crossing a particular location at 11 a.m. in the morning, exactly at the same 11 a.m. it actually crosses that part. So that's what we call as the sun synchronous, and we have this ascending and the descending path. During the ascending path, satellite will be on the darker side, so there is no remote sensing phenomena, while during the descending path they are more toward the sunlit side and the process of remote sensing take place. So most of these satellites what we call as the polar satellites, they circle at the low altitude between 200 to 1000 kilometers. So most of our remote sensing satellites are polar to near polar satellites, capturing information about the surface of the Earth, providing very high resolution images. Sun synchronous, as I mentioned, those are the orbit which are actually the satellite orbital plane is placed in such a way that the satellite consistently passes over the same location at a given point in time at the same time during each orbit. So typically, as I mentioned, these sun synchronous orbits they are placed at a range between 600 to 800 kilometers above the surface of the Earth and complete the full orbit of the Earth in approximately 100 minutes. So depending upon the location of these orbits that are placed, we see there is a variation in the complete rotation of these satellites. So mostly these sun synchronous are useful in the weather monitoring and other remote sensing observations more on the natural resources, which actually provide different information time intervals and help us in monitoring the temporal changes.